we're going to assume what? Well, no adiabatic process. Adiabatic process. So, essentially, no heat transfer through my components. It's insulated. So, what are my conservation equations? So let's go back to mass conservation. And we said, well, dm dt is equal to m dot in minus m dot out. Well, steady state equals 0. So what do I get out of this? I get out of it m dot in is equal to m dot out. Okay, for most of my systems. First law of thermal. Well, I've got my rate of change for time that we just said that this is equal to 0 because it's steady state is equal to my q dot net plus let me move this up. My q dot net plus work dot net plus m dot enthalpy plus my kinetic energy, un squared over 2. I got rid of potential energy because I don't have to worry about it right now. M dot, this is in, out, h out, plus u out squared over 2. That's my first law. So that's equal to, now I said adiabatic, right? So if I assume adiabatic, then I'm just going to say equals to 0, adiabatic process. So from there, rearrange my terms. What am I going to get? I'm going to get 0 is equal to W net plus mass in versus mass out. Based on this one-dimensional form, if I'm not introducing any formula, I'm going to say m dot in is equal to m dot out. So these two are equal, so I could just say m dot. So I could say m dot in is equal to m dot out is equal to m dot. Okay, so m dot h in I needed a minus here. Needed a minus here. So minus m dot out, enthalpy out, plus the kinetic energy un squared over 2 minus the outlet kinetic energy of the system. So let's take it and apply it to some of our components in the engine. These are like the general forms of what we just wrote, applying it to the engine directly. One of the easiest components to apply it to is a nozzle. So let's start with a nozzle. Okay, so I've got a nozzle that looks like this. I'm going to insulate it to have an adiabatic process. And I've got, starting from station 1, going to station 2. And by applying the equations that we just wrote for conservation of mass, which is right here, and my energy, did I count for conservation of mass in there? Yes. Do I have shaft work in there? No, right? I don't have to worry about shaft work. There's no shaft work. There's no mechanical work. Okay? So what do I have to worry about? It's just the rate of change in enthalpy and kinetic energy. One second. So if I write this equation and say, well, if I take mass and energy, I just have to worry about my rate of change of enthalpy. So m dot h in minus h out plus un squared minus u out squared is equal to 0. So if I apply it to my problem, what am I going to get? I could just get rid of this and say h1 minus h2 is equal to half u squared minus u1 squared. So simply the enthalpy change across this nozzle is driven by the rate of change in kinetic energy. Okay? We got a question.
Is that U, the E, what we were calling E?
No, this is velocity, kinetic energy.
Okay.
Good question. Right? But don't get lost. Where did this come from? Everybody knows where this came from? Right? Let me pull it up. Where it is right here. This equation right here that I just talked about this morning. Right? It's m dot enthalpy, kinetic energy, and potential energy. What is kinetic energy? Write it down right now. Half v squared. This is velocity. So don't get confused. I kept so our internal energy is E. I think I kept most of our symbols that internal energy is E. I'm hoping because we always confuse it with U, but we don't want to use U because U is always velocity for our case. Okay? But kinetic energy. So this equation is the same as this equation. The difference is I set potential energy 0. I have to do with kinetic energy, which is, think of your half rho v squared from your Bernoulli's equation that you're used to. It's the same principle. And that's your kinetic energy multiplied by enthalpy. So I have enthalpy multiplied by kinetic energy. Any further questions on it? So if I applied it to this system, right, I get the rate of change in enthalpy is equal to my kinetic energy. I have no work being done here. I have my flow work. Where's my flow work? Do I have work being done here? Yes. Confirmed it for me. Yes. So, do I have work being done here? So I don't have mechanical work, shaft work, right? But what do I have as work being done? Boundary work. And how did I count for boundary work? Did I have to do the integration of P dV every time? No. How did I capture it? Enthalpy. Enthalpy is what? Internal energy plus PV. Right? Just wrote that equation here somewhere. So yeah, we have to make sure that we understand that I have flow work, I have work being done. Enthalpy is internal energy, E plus PV. And I count it through my boundary work, which is an integration phase, PV multiplied by mass. So I took that, and instead of actually writing it out every time that I have to account for flow work, as I mentioned, the medium that we're working with is fluids, and fluids are deformable. So it's a complex base medium that I have to deal with. So instead of just dealing with that integration, we simplified it by lumping it in with the enthalpy. So now I'm accounting for enthalpy changes. And we know that enthalpy is what? In terms of specific heat.
CPDT.
Yeah, CP delta T. Right? Where is
You have 2 videos? I don't know what to pass it.
right here. CP is equal to dH over delta
Oh
T.
boy,
So
interesting.
if I say rate of change in enthalpy is equal to CP delta T. Rate of change of an internal energy is equal to Cp delta T. So what is enthalpy accounting for? The rate of change of heat within the fluid as a result of the boundary changes. So if I look at this problem again, this nozzle, what is really happening as I'm going through this? From here to here, what's happening to velocity? It's increasing. However, the gas or the medium that I have to deal with inside is actually experiencing a rise or a rate of change in temperature due to my boundary work. These are actually getting closer to each other, and that boundary work is accounted through my temperature change. Make sense? All right. Let's characterize the efficiency of this system now. And say, well, let me draw my enthalpy entropy diagram because I understand that I might have a non-isentropic process. So what is happening here? I got two pressure levels, some P. Which is high pressure and which is low pressure? Assuming this is subsonic. You guys are aero. You should know this already. Subsonic flow going through a nozzle. Which is the higher pressure and which is the lower pressure? So when I was an undergrad, I used to get confused because it's like it's going through a nozzle, right? So you would think the pressure will rise when it gets to the exit. But think of this: your garden hose. What happens when you actually put a nozzle at the end of it? It speeds up, right? So what does that mean about the velocity at the end, at the exit? Higher. So when the velocity is up, what happens to pressure? It goes down. So remember that garden hose. That's my reference to date, actually. So whenever I get confused, I think of that garden hose. Velocity goes up or down. So velocity here is higher. So velocity here is high. Pressure is low. Pressure is low. Here, velocity is low. Pressure is high. So this is P2 or P1? P1. This is P2. Right? Makes sense? The pressure is higher as it comes in, and it decreases as it goes through the nozzle. So I'm starting from station 1 right here. The isentropic process where entropy is 0. I have no heat primarily that is being transferred to the gas itself. Straightforward to 2. This is the isentropic process. And we're going to call this 2S as being your isentropic reversible process. But that's not what happens through a nozzle. We know that I get an actual process that looks like this. 2 actual. So this is isentropic. Remember this, right? So this is the real deal.
Actual isentropic.
This
Where?
is isentropic.
Isentropic.
No, at the bottom.
Actual? What are you talking about?
So, what does
2A,
that mean
2S?
about my overall efficiency? Well, my overall efficiency is, for the nozzle, is going to equal to what relative to what? So let's say enthalpies. Enthalpy divided by enthalpy. And we know efficiency cannot be greater than 1, so it has to be less than 1. So I want you've seen this before, in thermo, high-speed aero, in heat transfer, but how do I put these subscripts there? So it's probably H minus.
It's H2A minus H1 over H2S, so minus H1.
So let's walk through what our colleague said. It's H2A minus what?
H1.
Minus H1. So where's H2A? Let's make sense of that. H2A is down here.